Day 735 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again another day, another LeetCode problem where we're doing daily LeetCode problems. And today we have question number 3629, minimum jumps to reach and via prime teleportation. The difficulty level is medium, but don't worry because you already know we're going to keep the solution as simple and easy to understand as possible. But before we get started, y'all, don't forget to like, hype, subscribe, comment, and share. And if you need any new Apple AirPods, go ahead and check out that link in the description so you can get you some. Now let's see what the question says. You are given an integer array nums of length n. You start at index 0 and your goal is to reach index n minus 1. From any index I, you may perform one of the following operations. Adjacent step, you could jump to an index I plus 1 or I minus 1 if the index is within bounds. Prime teleportation. If nums of I is a prime number p, you may instantly jump to any index j where j does not equal I such that j nums of j mod p is equal to 0. Return the minimum number of jumps required to reach index n minus 1. All right, y'all, so that may seem a little bit confusing at first, so let's go ahead and take a look at these examples just to make sure that we are doing this problem correctly. So, in example 1, we have our input. Sorry, y'all, let's bring this down here. In example 1, we have our input nums equals an array of integers 1, 2, 4, and 6. Our output is 2. Explanation says one optimal sequence is we could start at index I, which is 0, take an adjacent step to index 1. So we can perform this adjacent step operation and we can move from here to here because that's an adjacent step. That would be I plus 1. Boom. So now we're right here. Then at index I equals 1, nums of I equals 2 is a prime number. Therefore, we can teleport to I equals 3 as nums of I is equal to 3, or nums of 3 is equal to 6 is divisible by 2. Thus, the answer is 2. So, boom, we're right here. Boom, after this first adjacent step operation, we're right here. Boom, then we could, since this number is prime, we could jump all the way here because this prime number, or excuse me, this number is divisible by this prime number, right? We could divide 6 by 2 and the remainder would be 0. So it's divisible, right? So then that means we made it to n minus 1 after that jump, and we were able to do that in 2 jumps. Now, just in case that didn't make sense to y'all, let's take a look at example 2. So in example 2, we have our input nums equals an array of integers 2, 3, 4, 7, 9. The output is 2 again. So let's look at explanation to see how we got this output from this input right here. Sorry, y'all. Boom. So it says one optimal sequence of jumps is first, we're going to start at index 0, I equals 0 and take an adjacent step to index I equals 1. So once again, we're going to start here. We're going to perform this adjacent step operation, I plus 1. And then, so we're going to move here. Boom. Now we're right here. And as you can see, we already see that this is a prime number and this is divisible by that prime number. But let's go through the example anyway. It says at index I equals 1, nums of 1 equals 3 is a prime number. Therefore, we teleport to index I equals 4 since nums of 4 is equal to 9 is divisible by 3. So once again, after the first operation, we land here. 3 is a prime number. This element at the end of the array, right? We want to make it to n minus 1. So since this is where we want to make it to, and this is, or excuse me, 3, or yeah, this is divisible by 3, we're able to make that jump, and we were able to do that in 2 operations. Thus, the answer is 2. So let's take a look at example 3. So in example 3, the input nums equals an array of integers 4, 6, 5, 8. This time the answer is 3. It says, since no teleportation is possible, we move through indexes 0, 1, 2, and 3. Thus the answer is 3. So we won't be able to teleport in this array. So we just move down. First we move here. That's one operation. Then we move here. That's a second operation. Then we move here. That's a third operation. Those were all using the adjacent step operations. And in total, we needed 3 of those. So that's why our output is 3, y'all. Boom. So I hope that makes sense to y'all. And now that we understand the question, let's get into the fun part, the actual solution. The solution is a little bit lengthy today, but it's all right. We will get through it, y'all. Just make sure y'all stick around to the end to make sure that we get through it. Boom. So first thing we're going to do is we need to get the total number of elements. So we're just going to say let n equal nums.count. Boom. Then if there's only one element, we already at the destination. So we can say if n equals 1, then we could open up the brackets and we could return 0 right away. Boom. Then we need to find the maximum value in nums, and this will be used for building our sieve. So we're going to say let max val equal nums dot max, put the parentheses, question mark, 0. Boom. Now we need to get the smallest prime factor array. So we're going to declare a variable called SPF for smallest prime factor. We're going to set that equal to an array. Open up the parentheses. It's going to be repeating, colon 0, comma, count, colon max, val, plus 1. Boom. And now it's time to build our SPF sieve only if max val is greater than or equal to 2. Or sieve. Sorry, y'all, I don't know how to pronounce that word. Sieve is spelled like this. Boom. So we're about to build it. Boom. So we're going to say if max val is greater than or equal to 2, we're going to open up the brackets. And for I and 2 max val, we're going to open up the brackets again. And if it's still 0, then I is prime. So we're going to say if SPF square bracket I equals 0, we're going to open up the brackets and we're going to say SPF square bracket I. We're going to set that equal to I. Boom. And we're going to mark multiples of I. So we'll come underneath this and we'll say if I is less than or equal to max val divided by I, then we'll open up the brackets and we'll declare a variable called j and set that equal to I times I. Then we'll come underneath that and we'll say while j is less than or equal to max val, we'll open up some more brackets and only set if not already assigned. So we'll say if SPF square bracket j equals 0, we'll open up the brackets and we'll say SPF square bracket j, we'll set that equal to I. Boom. Then we're going to come underneath this and we're going to increment j by saying j plus equals I. Boom. Then we're going to come all the way down here. Sorry, make sure that's right. And we're going to create a dictionary for prime factor list of indices that are divisible by that prime. So we're going to declare a variable called prime to indices. Hold on, indices. Sorry, y'all. And we're going to set that equal to is going to be a dictionary, integer, colon. So the key is an integer, the value is an integer. And, the value should be an array of integers. So boom, it should look like this. Boom. And then put the parentheses to initialize it. Now we're going to process every number in nums. So we're going to say for I and 0 less than n. We're going to open up the brackets. And we're going to get the current number to factorize. So we're going to declare a variable called x and set that equal to nums square bracket I. Boom. Then we need to prevent duplicate prime factors. So we're going to declare a variable called used primes, set that equal to a set of integers. So set less than int greater than, put the parentheses. Boom. Now we need to extract prime factors using our SPF. So we'll come underneath this and we'll say while x is greater than 1, we'll open up the brackets and we're going to say let p equal SPF square bracket x, come underneath this, and we're going to add the index only once per prime. So we'll say if exclamation point used primes dot contains, open up the parentheses, passing p, then we'll open up the brackets, and we'll say prime two indices, square bracket p, comma default, colon, a blank array, come outside both those square brackets right here, and we're going to append, open up the parentheses, passing I. Then we're going to come underneath that, and we're going to say used primes dot insert, open up the parentheses, passing p. Boom. Then we're going to come underneath this, and we're going to remove one prime factor by saying x divided by equals p. Boom. Now we need to set up our BFS. So we're going to come right here, and we're going to create a queue by declaring a variable called q, set that equal to square bracket 0, come underneath that, and we're going to track the visited indices by declaring a variable called visited, set that equal to an array, open up the parentheses, repeating, colon, false, comma, count, colon, n, come underneath this, and we're going to start at index 0. So we're going to say visited, square bracket 0, we're going to set that equal to true. Boom. Oh, sorry, y'all. We're not, well, yeah, sorry. Yeah, that's right. We are going to set that equal to true. Boom. Then, let me make sure everything's right. There's a lot of code. We're going to come underneath this and create a pointer for the queue traversal. So we'll declare a variable called front, and we'll set that equal to 0. And then we need the number of jumps taken, so we'll declare a variable called steps, set that equal to 0. Now we need our standard BFS loop. So we're going to say while front is less than q dot count, we are going to open up the brackets, and the number of nodes at the current BFS level, we're going to say let size equal q dot count minus front. Boom. And then we're going to process all nodes in the current level by coming underneath this, and we'll say for underscore n 0 dot dot less than size. We're going to open up the brackets, and we are going to say let I equal q square bracket front, come underneath that, and we're going to say increment front by saying front plus equals 1. Boom. And if we reach the last index, we're going to return the number of steps by coming underneath this, and we're going to say if I equals n minus 1, we'll open up the brackets, and we can return steps. Now we need to track our adjacent steps. So we're going to come underneath this, and we're going to say let neighbors equal square bracket I minus 1, come outside of, or excuse me, comma, I plus 1. Boom. Then we'll come underneath this, and we'll say for next in neighbors. We'll open up the bracket, and we need to ensure a valid index and not, it's a valid index and not visited. So we'll say if next is greater than or equal to 0, and two and signs, next is less than n, and two more and signs, exclamation point visited square bracket next. We'll come outside of that, open up the brackets, and we'll say visited square bracket next equals true. come underneath that and we'll say Q dot append, open up the parentheses, pass in next. Boom. Now we're going to handle our prime teleportation by coming underneath this, and we'll say let value equal nums square bracket I. Boom. And we're going to teleport only if the current value itself is prime. So we're going to come underneath this and we're going to say if value is greater than or equal to 2 and two and signs SPF square bracket value, come outside of that, equals value. Then we'll open up the brackets and we'll get all indices divisible by this prime. So we'll say if let indices equals prime to indices square bracket value, come outside of that, open up the brackets and we'll say for next in indices, we'll open up the brackets and visit the unvisit indices. So we'll say if underscore visited square bracket next, come outside of that, open up the brackets, we're going to say visited square bracket next, we're going to set that equal to true. Come underneath that, we're going to say Q dot append, open up the parentheses, pass in next. And then we need to clear the list after processing so we never process this prime again. And this is going to prevent big O of n squared behavior. So we'll come underneath this right here and we're going to say prime to indices square bracket value, come outside of that, set that equal to square bracket, boom. And then we're going to come down here, we're going to increment steps by saying steps plus equals 1. Then we're going to come underneath this and we're going to return -1 if the destination cannot be reached. So that should be all she wrote. Let's give it a run. See how it runs. Oh, it's accepted on the first try. That's what I'm talking about. That's a lot of code to get accepted on the first try, y'all. Let's see if it's still accepted after we submit it. Let's see. And look at that, y'all. 824 milliseconds beats 50% of users. Not too bad, not too bad at all, y'all. So before we go, make sure you get one more look at the code. I know it's a lot. This is the top part. This is like the top of the middle. This right here is probably like the middle of the middle. This right here is probably like the bottom of the middle. This right here should be the rest of the code. If you ain't get that part, then this right here is the rest of the code, y'all. And yeah, with that being said, y'all, I hope y'all learned something today, and I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.